what is intrinsic. So you have the pure semiconductor. So silicon intrinsic semiconductor means that it is pure and without adding any impurity atom. Okay, if you have silicon crystalline, so that is totally silicon intrinsic. Okay, intrinsic semiconductor. And then you have a doping process. So you dope that intrinsic semiconductor or pure semiconductor with an atom. So there are two type of material where they call it as a trivalent, okay, trivalent material and pentavalent. Trivalent means it has 3 valence electron and pentavalent means it has 5 valence electron. So you dope with that pure semiconductor. So what happens? So semiconductor, we know that it has 4 valence electron. When it is doped with a trivalent atom, so it has one left hole. Okay, so if you imagine it is being doped with too many silicon, so there will be many holes. Okay, many holes. So because of this atom is called as acceptor. So it tend to accept electron to fill up the hole. Okay, so this one will produce the majority carrier holes and it will develop the p-type. Okay, the p-type semiconductor. Okay, p-type semiconductor, p. Okay, p-type. So for the n-type, when you have silicon, okay, silicon dope, the doping process dope with the pentavalent atom. So pentavalent have 5 valence electrons. So when silicon has 4 valence electron, dope with 5 valence electron, the complete shell is 8. So it has one excess electron. So if you imagine the silicon crystalline, so doped with pentavalent atom, it has a lot of donor atom, okay, donor electron. So if you can imagine, it actually creating a lot of free electron, okay, freely move here and there. So this type of doping will create the n-type semiconductor, okay, n-type semiconductor. So this doping will actually creating this p-type and n-type is actually extrinsic semiconductor. Okay, extrinsic semiconductor. So why we do doping process? Because we want to improve the connectivity. Okay, so now we would like to look at what happened if we brought together the Pn junction. Okay, so if you have p-type. Okay, if you still remember. So this is your p-type. Okay, P at the left and n-type. Okay, so what happened when we brought together these both p-type and n-type? Okay, what happened? So the purpose of this is to know the function of diode. Okay, if you still remember diode, okay, diode. So this is diode symbol. Okay, so diode is actually behind the symbol of behind the diode. It is actually the combination of P and n-type. Okay, P and n-type. So what happened to this diode? Okay, what happened to this diode when P and n-type are combined together? Okay, all right. Okay, so now the topic 2 is PN junction. So what happened when we brought together the p-type? What happened is what happened at this junction here. So now we are concerned about what happened at this junction. Okay, so this is PN junction. Okay, so this is the outline. Okay, the basic structure of PN junction. And then what happened when we didn't apply bias? Okay, what happened when we apply bias and forward bias to the PN junction? Also, the IV characteristic, the IV relationship. Okay, the current voltage relationship and the junction capacitance, the junction breakdown, and finally the summary. So junction means at the PN junction. Okay, so let's recall a bit. Okay, so this is the like I draw just now, so we have P region and N region. When we brought these two together, okay, we know that N region, the majority carrier is majority carrier is free electrons. Okay, while P region, the majority carrier is hole. Okay, if you can see in this figure. All right, so many electrons and many holes. Okay, so we brought together this, so there will Pn junction occur. So the concern is what happened inside this Pn junction. So without any bias, okay, we can see that this free electron is moving around, and this hole is moving, but in a slow steady mode, because hole is very very slow. So this electron is actually tend to attracted to the holes actually, naturally, without any bias. Okay, so this region is actually PN junction. The two material are joined together. Okay, so what happened in here? So this PN junction is actually serve a dividing line, okay, that marks the ending of one material that is doped in the N type, and the other type is P type. All right. Okay, at room temperature, okay, there are large of free electrons in the N region conduction band. I think you still remember this. And then these electrons are randomly moving around. Okay. All right. So at the instant PN junction formation, the diffusion takes place. Okay. So the diffusion takes place means, all right, um, means that naturally this electron will be attracted to the hole, because electron is negatively charged, holes is positively charged. So this, since it can freely moving around, so it tend to drift to the left side. Okay, so this what we call is either diffusion. Okay, diffusion, where all these free electrons are diffused towards the holes. Okay, because of its negatively charged. Okay, so this what it means by this statement. All right. So again, with the different concentration, and also because of the negatively charged, it tends to diffuse to the left side. Okay, so if you can see, if this shows this figure shows how the free electrons moving around, and some of it will be diffused towards the left side. Okay, if you can see here, if we talk about the electric field, so it looks like the electric field is moving. So the electric field, so if I write E and then an arrow like this, so this means as electric field. Okay, electric field. All right. So I have to tell this because since some of you in the background of computer engineering, so you might not know what is E and then slash arrow here. So this means the electric field. So if you can see here, so electric field is actually moving to the left direction. Okay, to the left direction from N type to the P type. So this is represents as the electric field of the electron. Okay, so when P junction forms, so holes from P type will diffuse to the N type, but very, very slow, because we know the acceleration for holes is slow. And then the electron from N type will diffuse to the P type. Okay, this is basically the nature, because of its negatively charged and positively charged will be attracted to each other. Okay, so the combination. Okay, so what happens here when all these free electrons, okay, moving to the left side, and holes tend to move to the N side? So what happened at this junction? So what happened at this junction? So it is actually the holes and electrons will be combined at this junction. Okay, when equilibrium reach, so means that the electron diffusion diffuse to the left side. Okay, so this diffuse will be stopped. Okay, there will be no further diffusion of electron. So what happened at when equilibrium reach? Okay, so this is what happened. So one, okay, it will become the minority carrier. So as electrons, the majority carrier moves across the junction, it will become minority carrier. And this electron will fall into holes near the P junction. Okay, so what happened here? Okay, what happened here? So when this electron move to the holes and fill up this hole. So if you can remember, this is the recombination process. So this electron is actually will leave a positively charged at this PN junction. So this is the yellow one is your PN junction. Now, when equilibrium when equilibrium reach, so this free electron who fill up the hole will leave a positively charged near the end region PN junction, whilst the holes who already being filled up with free electron will leave a negatively charged, okay, at the P region near the PN junction. Okay, as you can see, so this region is actually, we call it as depletion region. So why it is depletion region? Means it is depleted, okay, depleted. It is depleted, okay, means no majority carriers here. What is actually exists at this depletion region is just charges. Okay, charges means positively charged and negatively charged. So now what I meant here, the free electron here is a carrier. So majority carrier electron and majority carrier of holes. Okay, when it diffuse each other, so it will leave a charge. So this region is depleted region. Why it is depleted? Means it is zero carrier. Depletes mean nothing inside here. So no carrier inside here, but just the charges. Okay, when there is charges, okay, I'm explaining it step by step, okay, so that you understand the story behind it. So like I said that the electric field, okay, the electric field is from the N type to the P type. Okay, so this is the electric field. Okay, because of these charges, okay, because of these charges in this depletion region, so these charges might be attracted to each other because positively charged go to attracted to the negatively charged. So this actually created a potential barrier. Okay, potential barrier. So this potential barrier is actually due to the electric field, and this potential barrier is actually in terms of voltage. Okay, voltage. There is a voltage across this PN junction because of this depleted region. Okay, depleted region where it only exists with charges, and these charges are attracted to each other, and it will create a potential barrier. Okay, potential barrier means there is a voltage across this barrier. Okay, so what does this means by the potential barrier? It is actually mm, the difference of potential between PN junction across the depletion region. So this what it means by the potential barrier. All right. So this statement I have explained just now. So if you do your um, revision, okay, you can read again. Okay, so this is what I have explained here. So these are the story, how the depletion region created, and where does the potential barrier coming from? It is because of the attraction between this positively charged and negatively charged. Okay, and because of this, okay, barrier also is due to the electric field. Okay, where all the majority carrier electron are diffused to the left side. So this will create an electric field. All right. Okay, so we might ask you a very simple question. What is depleted of depletion region? So depletion region here means it is depleted of charge carrier. Means it is zero, nothing inside here. Okay, no carrier, no free electron. Okay, but only charges inside it. Okay, and this depletion region is formed very quickly. Okay, why? Once a Pn junction brought together, it is automatically this free electron will be diffused toward these holes. Okay, so this when this Pn junction brought together, it is abruptly sudden creation of this depletion region. That's why it said here, it is very quickly and very thin. All right. So this is the figure. Okay. If I can show you, so the left figure. So this is actually what I have shown you just now. It's just that the PN junction brought together. So this is the PN junction. Okay. Okay, if we could draw this, so this figure, this left figure is actually the simplified geometry. Okay, the doping profile. Okay, we know that the left side is N region where a lot of donor. Okay, concentration where the concentration is represent as ND. Okay, I have to slow down and go step by step because some of you didn't familiar with this. Okay, so ND. Okay, so ND. Okay, so ND is actually concentration for donor. Okay, doping concentration for donor. Okay, donor atom. Why donor atom? You know, because this is N-type. Okay, so Na. Okay, I think not only for those who's not familiar with this term. I think for those who already taken, you might also as well forget about this term. Okay, so let's just slow down and we go slowly together. Okay, so this is doping concentration. Okay, concentration for acceptor. So it is represent as Na. Okay, Na. Okay. So if you look together here, so this is doping concentration. So this is at the junction. So this is the doping concentration for donor. This is doping concentration for acceptor. So as you can see here, like I said, the electron is diffused to the left and hole is diffused to the right. So electron tend to diffuse much faster than the holes, okay, because holes moving slow. Okay, so if you could draw this again, what happened when it brought together, it is actually creating a depletion region. Okay, so if you learn in your undergraduate, so in undergraduate, so it is actually known as a depletion region. Okay, like I've shown here in this figure. But if you learn in higher level, okay, they call it as a space charge region. Okay, space charge region. Why does it call by space charge region? Because this region, okay, this depletion region is only it is the space for charge located. Okay, so as we can see, so positively charged is located near the N junction N region, and negatively charged is created near the P region. So that's why it is called as a space charge region. Okay, so this region has electric field. Okay, this is the electric field moving from the right to the left, which is how I've explained just now. It is actually the electric field where the for electron movement. Okay, electron movement. Okay, electron movement. Okay, so this electric field is actually due to the diffusion, okay, the fusion of free electrons. Okay, this is what, okay, why is this figure important? Because since the space charge region is depleted by the charges, okay, Okay, this density gradient still exists in the majority carriers concentration at the edge of the space charge region. This one, the density gradient. So this is what happened behind the PN junction. Okay, inside this PN junction, so this is what happens. Okay, where the space charge region exists. Okay, and there is the electric field inside this. So this electric field is due to the attraction of positively charged and negatively charged. All right. Okay. So what happened? Okay. Okay. So this is two type. So what happened when we brought together the PN junction? Okay. There are two type of biasing. Okay. There are two type of biasing. So biasing in PN junction. Okay. There are two type. Okay. One is okay, so number one is forward bias. When I write FB means forward bias. Okay. And number two is RB, it is reverse bias. Okay, so PN junction. So why we want to make it forward bias, reverse bias? Okay, let's go back to the basic. So when you have a diode, okay, so diode means you want to allow current to flow through the circuit. Okay, for example, you have like a very simple circuit like this. So you have voltage supply here. Okay, this is your voltage, and then this is your diode, and then this is your resistor. Okay, this is your diode. Okay, diode. So it tends, so in this case, okay, we tend to make the current flow through very smooth, so we use diode. Okay, in order to make this current I to flow through this diode, we need to place this diode in forward bias, or in other word, in on state. Okay, in on state. So how to make this this PN junction, okay, forward bias or reverse bias, is by applying the right voltage to this PN junction. Okay, let's take a look here. Okay, if we apply a positive voltage to this P type, and we apply negative voltage, so this is your voltage apply, so voltage, so this is also your voltage. So if we apply negative voltage to the N type, means you are creating this system as in forward bias. Okay, forward bias. So what happened to this depletion region when it is in forward bias? Okay, so we know that um, in N-type, we have, I think you have know this, but it's okay. So this is free electrons. Okay, a lot of free electron moving around at the N-type, and a lot of holes are moving around at the P-type. So these electrons, okay, because of this positively biased here, okay, you have a high positive plate, positive terminal here. So very high positive voltage. So these electrons, which is this electron that negatively charged, it tend to be attracted to this positive plate. Okay, to this outer terminal positive plate. So it tend to be attracted to this positive plate. However, the holes tend to be attracted to this negatively plate. Okay, okay, negative plate. So this is positive plate. So because of this voltage bias is increasing, so this tend to be attracted each other. So what happened to this depletion region? So this depletion region will become thinner. Okay, this depletion region will become thinner. Okay, thinner. And when this depletion region thinner, so the voltage barrier, okay, the potential barrier decreases. Okay, decreases. So this barrier decreases. Okay, because of this, barrier decreases, then it actually tend to create the current, okay, can pass through this barrier, and you can actually measure the current at this diode. Okay, at this diode, so current can pass through this. Okay, okay, current can So current can pass through this barrier because of this barrier, thin barrier. Okay, so because of this, okay, you are tend to create this region. So where does this, if you can see this IV characteristic, okay, so this is the IV characteristic for PN junction or diode. Okay, as you can see, if you look at the forward bias, okay, so the right side here is for the forward bias case. Okay, as you can see here, okay, the forward bias. So from 0, so this voltage is actually the application of this voltage bias. Okay, as you increase the voltage, this barrier, this depletion region will become thinner and this barrier will reduce. Okay, when there is reduced, then you can actually get current increase. Okay, so current start increase when you apply greater bias voltage to this PN junction. Okay, so what does this knee voltage? So this is actually the knee voltage, or actually the voltage of this potential barrier. Okay, the voltage of this potential barrier. If you apply this voltage greater than this potential barrier voltage, then the current start increasing. Okay, until it reach the potential barrier voltage, then current start increasing. Okay, so this is what happened during forward bias. So if you ask to draw the characteristic, the IV characteristic of the diode, so this is for the case of forward bias. So what happened? I think you can imagine the vice versa case for the reverse bias. Okay, for the reverse bias. So what happened for reverse bias? We applied vice versa voltage. Okay, vice versa voltage. So you have instead, so the P type you apply negative. Okay, for this case forward bias you apply positive. Okay, for the N type, for forward bias, you apply negative. Now we apply positive. So now you can imagine a vice versa situation. Okay, opposite situation will occur here. Okay, during reverse bias, where you have in N type, you have a lot of free electrons. Okay, now this free electron is negative. It is not moving to this side because of this positive lip plate, okay, positive charge terminal here. So this free electron tends to move to this positive plate. Okay, so as this hole, okay, tends to move to this negative plate, especially when we increase the voltage. So what happened to this depletion region? So now this depletion region will become wider. Okay, when this depletion region become wider, so this barrier is actually increasing. Okay, increasing. Okay, so for this case, forward bias, sorry, I have to go back. The diode is on. Okay, for this case, because of this increased barrier, so it is actually cannot, this is actually, this diode is actually not turning on. So it is actually become open circuit. Okay, open circuit because of this large barrier. So electron cannot pass through and you are actually cannot measure any current during this case. Okay, so in here it is actually current equal to 0, approximately equal to 0. Okay, so for this case is actually diode is behave like off. Okay, behave like off. So that's why, okay, if you can see here, so this is the left side here is for the case of reverse bias. Okay, where there is no current can be measured. Okay, there is no current can be measured. It is approximately equal to 0. If you increase further this voltage, negatively voltage increase further, so more negative. Okay, so if you can see here, it is actually there is a small value of current, but ideally we consider it as 0. Okay, 0. So it is actually, there is a small reverse current exists here. Okay. Okay, but very, very small. Okay, very, very small. So sometimes for ideal case, we consider it as 0. Okay, 0 ampere. All right. So now, okay, now this is the real business, okay, in this subject. So, the Venn diagram, okay, the Venn diagram. So, if you, okay, if I just want to tell you that most of the question, okay, in the test of final exam, you will be asked to draw the energy band diagram. Okay, so these are called the energy band diagram. Okay, so in this topic, starting from Pn junction, or later in the MOSFET, in the next chapter, we will bring this concept of energy band diagram into the next chapter. So let's start with how to draw the energy band diagram. Okay, I repeat that most of the question, okay, will be asked you to draw this energy band diagram. Okay, although since this is an online test or online final exam, we don't know, but still you need to know how this energy band diagram is brought up. Okay, so this energy band diagram, so I'll show you the PN junction. Okay, what happened inside here? Okay, what happened inside here where all the okay, the diffusion takes place, and then we know that this N region where if you still remember the conduction band, where the at this region we know that free electrons are moving around. So we know that free electron is actually the electron at the conduction band. So what happened when this free electron moving diffuse to the left side, okay, going moving around? So what happened inside here is it actually represent as this energy band diagram. Okay, in general, if we draw the energy band diagram, we will start with the vacuum level. Okay, so this is the vacuum level. So vacuum level is actually, so this is your conduction band. Okay, this is your conduction band. So this is your valence band. Okay, so we always draw in the textbook, always draw with the vacuum level, means up to now we only know that the conduction band is the maximum shell, but then there is a vacuum level, okay, where above the conduction band. Okay, because of this vacuum level, okay, vacuum level, we took it as a reference point. Okay, so from this vacuum level, okay, to the conduction band, we call it as a chi. Chi. So this represent as a voltage value. So this chi value, okay, chi value, or we name it as a electron affinity rule. Okay, later I'll show you what does this mean. Okay, electron affinity rule. So in this region, okay, this energy band diagram, we call it as a flat band. Okay, flat, everything flat. Okay, means that there is no moving around of free electron yet. Okay, what is inside the energy band diagram? You have what vacuum level, and then you have EC at conduction band. What does this means by energy at conduction band? E is represent as energy at conduction band. Okay, and then at valence band, okay, we have EV, where energy at valence band. Okay, so when these two takes place, okay, we also have energy, we also has Fermi level energy at N type, represent as, so this is actually subscript. You see this actually represent as EFN, small subscript. So this is energy FP, okay? Energy, Fermi level energy at P type. This one, Fermi level energy at N type. Okay, so these two, when EC minus EFN, so these are the different potential. So these are the different potential EFP minus EV. So what is EG? I think you still remember. So EG is band gap. Okay, band gap. What is band gap? It is actually EC minus EV. I think you know this. We have looked at the example in the previous lecture. So band gap is EC minus EV. All right. So what happened? Okay, just now it is at flat band. Okay, these two are not combined yet. So what happened when we combine these two? Okay, so when the system reach thermal equilibrium. Okay, what is thermal equilibrium? Let's go back to here. So thermal equilibrium means there is no diffusion occurred yet. So all the diffusion stop. Okay, all the diffusion stop. So what happened when all the diffusion stop? Okay, it is actually here. All the diffusion stops. So what happened in here? So wait. Okay. So what happened? All this diffusion stop. Okay, so the EC, okay, brought together here. So now this junction takes place. Okay, there is no Fermi level. Okay, so now when the diffusion stops, so the Fermi level energy at n type will align together like this. Okay, in the same level of the Fermi level at the p type. Okay, because this EF alignment is achieved by the carrier movement from high energy to low energy. We imagine that. So at thermal equilibrium, so diffusion of electrons stop. So this Fermi level will be aligned together. So as you can see, now that the difference of EC minus EFN is equal to this portion and EF minus EV is equal to this portion, right? Okay, so again, okay, there is no difference in Fermi level because the EFN is now line up together with the EFP. Okay, now the difference of this right side EC and the left side EC. So this is also EC at the left side. Okay. And this is also EV at the left side. Okay, so this different EC at the left side and right side, we call it as a barrier potential, VBI. So where does this barrier potential? If we go back to this figure, this is actually the barrier potential at this region. Okay, at this region. So now we are actually drawing the energy band diagram at N region and energy band diagram at P region. These two brought together and it will create a potential barrier. So this potential barrier in energy band diagram represent as built-in voltage, VBI. Okay, so you will be using these terms, okay, from now on to this chapter and the next chapter. So this potential difference of EC at the right side and EC at the left side, we call it as VBI. Okay. All right, so this is when the diffusion takes place, okay, where is no bending yet. So this is what we call is as a flat band. So this is flat band, okay, flat band diagram. Okay, so next, so now at thermal equilibrium, okay, so this is the real energy band diagram of Pn junction at thermal equilibrium. If you can see, there is difference between this flat band diagram and this diagram. As you can see, there is a bending, okay, there is a bending going downward, okay, from the right side EC to the left side EC. Okay, EC means the energy at conduction band. So this is energy at conduction band. So this is energy at valence band, left side and P side. Okay, as you can see here, it is actually going down here. Okay, what does this represent? Okay, why is it going down? Okay, I have read some book and also watched some video. Why it is bending down? Because we know that, okay, okay, we always go back to this figure. Okay, we always go back to the figure. Okay, so we know that the right side is electrons. Okay, the free electrons. Okay, the left side is holes. Okay, we know that the concentration of holes is always majority carrier of hole is always less than the electrons concentration. Okay, so now electron is going towards the hole. Okay, the case is now that electron is moving faster, it is moving towards hole. Okay, because of this, okay, because of this, that's why this energy band diagram looks like this. Okay, we know that the concentration of hole is less than the concentration of electrons, and all the electrons here is actually moving towards the holes. Okay, moving towards the hole. So it is actually electron, okay, electron going down. Okay, electron diffuse actually. Because of this, it is going downward. This junction going downward. Okay, so if you know, if you understand what I have explained just now, what is actually this region going downward? It is actually the space charge region. Okay, the space charge region. This is actually the space charge region. All right, and some book said that this is a space charge width. Okay, width. Some book use width, some books use region, but it's actually the same. Okay, in the lower level, we call it, in the lower level or in undergraduate, we call it as a depletion region. In upper level, okay, we call it as a space charge region. So this region is actually the space charge region. Okay, so width of depletion. Okay, we know that we have the N type and P type. So this represent as so we know that this is p-type, this is n-type. So this is represent as xn. This is the width charge represent as xp. Okay, so width is actually, okay, the total width is actually xn plus xp. Oops. All right. Okay, so I hope that by a very step by step explaining this energy band diagram from flat band, okay, to the real energy band diagram, okay, where it is Pn junction. So I hope that you understand how to draw it. Okay, so remember that at thermal equilibrium, so this Fermi level of the diffusion stop. Okay, and the Fermi level at n-type is at the same level of the Fermi level at p-type, because at equilibrium, the diffusion stop where no electron moving around means that all has been filled up. Okay, so this Fermi level of n-type will be lined up to the p-type, same type. Okay, and this EC will be going down to the EC of p-type because electron is moving around, diffuse towards the hole. Okay. All right. So the built-in potential, okay, if you could draw it, okay, so this is from vacuum level to the EC, we call it as a chi, okay, okay, chi or electron affinity, okay. So this represent as electron affinity. Okay, so I hope that you already familiar. So this is the portion, this portion is EC minus EFN. And there is another terms, okay, another terms which is phi Fn. Okay, phi Fn is actually the potential, okay, the potential Fermi level at n type. Okay, phi Fp is actually potential at p type. So finally, the VB in, okay, we know that the VB in is EC at n type minus EC at p type. So where does this coming from? It is actually equals to phi Fn plus 5Fp. So this VB in is equal to the potential at Fermi at n type plus potential Fermi at the p type. Okay, so like I said, built-in potential is represent as the difference of Fermi level at n type and p type. VBI. Okay, so this VBI, okay, if you so this equation is actually given in the last class. We have used this. Okay, so this is concentration, okay, electron concentration at thermal equilibrium. Okay, like I said, 0 means at thermal equilibrium. I believe that you still remember this in the last class. So equals to the intrinsic concentration exponent EF minus Fermi level intrinsic over KT. If we rearrange this formula, okay, it is actually EF minus EFI, which is this portion is actually represent as phi Fn. Okay, phi Fn. So equal to this portion. And finally, phi Fn, we rearrange the formula, we will get equals to this equation. Okay, and this n initially was n is represent as Nd, and this is doping concentration donor. Okay, donor. All right. So this is for n type. So potential different, Fermi potential different at n type. Represent to the equation, this equation. And how about for the p type? Of course, we have this equation, okay, from the past lecture. Okay, if we rearrange, finally, you will get the phi Fp equal to this, where this is the doping concentration, okay, for acceptor. Okay. So finally, okay, we know that VBI, okay, is equal to the Fermi potential difference at n type plus Fermi potential difference at p type. Okay, if you combine these two, rearrange the equation, okay, of this portion and this portion, finally we will get the VBI equal to this equation, KT over electron mass, ln ND and NA over NI square. All right. This is very much a lot of lecture up to now. Do you want
Excuse
to
me,
have
Prof.
a, yes,
Just I want to ask you
yes, yes.
about the values. All these values will be given in the question.
Correct, correct, correct.
Uh, so as a table, or it will be straightforward in the question.
For example, this concentration, ND concentration and NA concentration, this one will be given in the question. Okay,
Okay.
but the rest, these are actually the constant value. This one will be given in the appendix, in the table sheet, like I shown you in the previous class.
Okay.
Do you remember?
Yes, yeah, I remember.
All right.
So
Okay.
about
Great.
E and Ni also the same.
I give yes, same.
Okay, thank you.
Mm-hmm. All right. So usually, okay. All right. Okay. I think I stop here. We have a 5-minute break before I continue with the example. Okay. I think we have a lot of explaining here. So let's take a look example in the next slide. I mean after break. Okay. Let's take a break. 5 minutes.
Yes,
Okay.
thank you so much.
Okay, doctor. Thank you.
All right. Okay.
I think by solving one question at least, one example, it will be more clearer for us.
Yeah, yes, correct. After
Yeah.
this, we look example, okay?
Yes, thank you so
Mr.
much.
Taha, all right, okay.
Thank you so much.
All right. So we take a look example after this, Mr. Taha, and let's have a drink first. 5-minute break.
Yes, yeah, thank you so
Okay.
much.
For those who are from computer engineering background, do you find this very heavy to accept this early morning?
Actually, it's the best time for studying like this subject.
Yeah,
But
this hour.
yeah, many terms and many things we are not familiar with.
Yeah,
So
yeah, yeah.
it's very difficult for us.
But that's why I go through slowly so that
Yeah.
you can catch up. I think not only you, I think for those who have learned also
Yeah,
might forget.
yeah.
Yes, yeah, it's long time because
New
I
information, Doctor.
Yes.
and also we graduated maybe before more than 10 years or something like that. So
Really?
yeah,
Really? Oh,
Yeah, about me, Doctor, before 15.
wow.
yeah,
Really?
it-
Okay, okay, okay. But that's okay. There's no always no stop in learning, right? But
yeah.
yeah, I'm so respect all of you.
Thank you so much.
I mean, you decided to study again, go back to all this.
Yeah, it's important. But we didn't know we will have something like this course, because it's
Really?
yeah more related to
Yeah, 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 yeah.
electrician. Ah,
Because
but
your background is computer engineering, right?
computer. Yeah.
Mm. You know,
Sometimes I mean sometimes in during undergraduate or something in high school, I think we have studied something like this in chemistry and physics. So we have some ideas, but definitely we cannot go advanced.
I know, I know, I know. You have some idea, but you don't know what is all
Yeah,
about.
yes, yeah,
But I hope that after this you have some idea. I mean, you clear. I mean, you at least have a little bit idea on what is electron,
yeah.
holes, Pn junction, so on, right?
And also, I wanted to ask you honestly,
Yeah,
when you
yeah.
when you were talking about the diode, and
Mhm.
when we passed the positive charge from P type.
Yes,
And
yes.
I think I remember if we passed, I think there will be a limited charge for n type. So if we put positive charge in n type and
Mm-hmm.
it was less than the, I don't know the term actually. I
Uh-huh.
think also it will be like open state or
Open
something.
circuit, open circuit.
I
Yes, yes,
remember
yes.
something like that, but I don't know how to
Ah,
use it.
means that your brain is still good. I
Yeah.
mean, still remember after 10 years back.
Yeah, I remember, but just I'm waiting to hear this information because
Okay, I hope I'm telling you. I hope what I told you, you recapture everything what you remember.
yeah,
All right, great, great. Mm. Because I don't know the rest. Who I think Taha and also Anwar is the background of computer engineering. How about the
computer.
rest? Mm-hmm. Like the others?
I also
Ah,
computer engineer.
oh, computer engineering, Mahir, computer engineering.
I'm
I
information
also.
science.
Oh, most of you. Okay, let's see who is from electronic background.
Me, doctor.
My Me,
Who? Me? Who's me? Can you
Tanro Pei.
Tanjope? And the other
Augustin.
one me?
Yes.
The one me just now? Who?
Zaur. Yes.
Zaur. Okay. Okay, 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 okay. All right, all right.
Ala,
Zaur.
teacher, also Ala.
Uh, again? Oh, Ala Kadim also electronics background. I see. Great, great. Okay. So at least we have it's okay, although I don't know, maybe you have forgotten. We go slow, okay, for every bit of the lecture so that everyone can remember the terms. How about Zafri Azman and Nurul
Um, I'm
Sabrina?
I'm from robotic mechatronic background.
Mechatronic background. I see.
I'm from instrumentation science.
Instrumentation science. Okay.
Yes.
But do you have you take electronic subject before during your undergraduate?
Yes.
I see. Okay.
Mostly similar.
Mostly similar. Oh,
Yes.
okay, 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 okay. All right. Mostly similar to this you learn here now.
Forward
Oh,
forward
great.
bias, with bias science.
From which university?
UPM.
Oh, UPM. I see. Okay, okay. All right, all right. So I think that yeah, for those not familiar, that's okay. I think this is nature. In the previous semester also, there are the other student from computer engineering background took this subject, and it is not impossible to get an A actually. So yeah, let's just give a try and put some interest in it. You'll be there, inshallah. Okay.
We hope,
All right.
inshallah, because we are afraid already.
All
No.
right. Okay. So I think we have done 5 minutes. Okay. If we can continue a bit, okay, maybe we can finish early. All right. Okay. We stop here just now. Okay. Let's take a look on the example. Okay. So calculate the. So this example said calculate built-in potential barrier. Okay,
I'm sorry, Prof. I
hello,
think you are not sharing your screen.
hello. Not
You
not
are not,
sharing.
not sharing,
Oh,
no.
okay, okay.
Not
Wait.
sharing. Yeah.
Oh, all right. Wait. Oh, not sharing. Okay. Oh, wait. Oh, okay. Yes. Not sharing. All right. How about now? Can you see example one?
Yes, we can.
All right. Okay. Right. Okay. So calculate the built-in potential barrier. Okay, to be familiar with. So I always want to write here. So built-in potential barrier represent as VBI. Okay, in NPN junction. Okay, consider a silicon. So type is silicon PN junction. Is silicon with a temperature 300 Kelvin and doping concentration, like I said, Mr. Taha asked just now. So concentrations are given. Okay, when concentration given, like Na is represent as acceptor concentration. Okay, Nd is represent as a donor concentration. Okay, so Na is 2 times 10 to the power of 17, Nd 10 to the power of 15. Okay, calculate the built-in potential. So the built-in potential is given by this equation. This equation. Okay, this equation Kt over E. Okay, so I think this part, okay, I always put this part as 0. Okay, if you can calculate Kt over E, it is actually approximately to 0.0259. Okay, so I usually in my slide I will put the value straight away. Okay, instead of plug in the K value, the T, and electron mass. Okay, so if you calculate again, okay, you can prove that this portion is equal to 0.0259. All right, so like I said, so all these concentration are given. So I think I have shown in the previous slide. Okay, I have shown in the previous slide. So in the previous lecture, so Ni is intrinsic, okay, intrinsic value. So let's just give a recall again. So this is your textbook, okay. If you scroll down this value, so if you scroll down, you can see that you can get so all this table will be given, okay, in the test and final exam. So intrinsic value is this part. So for this question is silicon. So silicon. So intrinsic value for silicon is 1.5 10 to the power of 10. Okay. So we will use this value, okay, and plug in into the equation. So this value is represent as 1.5 times to the power of 10. Okay, so finally you will get the built-in potential is equal to 0.713 volt. Okay, this is quite straightforward. Okay, quite straightforward question. But then, although if it is not straightforward, or all you need to do is just play around with the equation given. Okay, so you might have two type of equation. You have to solve equation. So again, in this topic, besides of understanding the theory part and everything, okay, it is actually 70% of it is calculation. Okay, calculation. So you can try plug in all the equation and try to calculate yourself. Okay, so for example, if we could if we change the doping concentration, so this is just an example, we change the doping concentration. For example, we reduce this this Na portion. So this built-in potential with this we actually changed decreased to 0.635 volts. Means that what are the conclusion from here? So meaning that if the concentration decreases, means that the barrier potential also decrease. Okay, so this barrier potential, so where does its barrier potential comes from? Is actually, so when the concentration at when the concentration here decreases, so concentration means the concentration of acceptor and concentration of donor decreases. So this is actually decreases the potential barrier. So like I said just now, this potential barrier is represent in the energy band diagram as a VBI. So means that this potential barrier or this VBI actually depends on the concentration, okay, of P region and N region. The less the concentration, the less the potential barrier. Why is this happen? Because the less concentration means that you are producing less number of carrier here, less number of carrier at N type and less number of carrier at P type. Therefore, this diffusion also less. So when diffusion less means less barrier potential, as well as the VBI. Okay, VBI is represent here at the energy band diagram. Okay. All right. So this is what this example means. Okay. If you want to understand behind this example, so this is actually that showing that the concentration is actually proportional. Okay. Okay. So the concentration Na or Nd is actually proportional to the VBI. Okay. All right. Now, the other term is electric field. Okay, I believe that I have explained just now what is electric field. Okay, I always like to go back. Okay, what is electric field? Okay, since all of you 10 years and 15 years back, so let's always go back here. So just recall for me also. So electric field is actually when this Pn junction takes place. Okay, so electron diffuse to from right diffuse to the left side. So it will left a positively charged, and this side will left with negatively charged. And this charge we call it as a space charge region. And electric field, I said, is the electron movement. Okay, electron movement, and also electric field also coming from the attraction of this charge. Okay, the attraction of this charge. So this charge here is actually attracted to the negative side like this. Because of the opposite charge, it is attracted to each other. So this will create an electric field. So how does the electric field distribution looks like? Okay. So how does the electric field looks like here at this space charge region? So there is electric field occurred here. So how does it look like is like this. So these figures, okay, shows this the space charge density, okay, in a uniformly doped Pn junction. Okay, we assume that there is abrupt junction, assuming abrupt junction approximation. Means abrupt junction means there is a sudden change in junction. Means this one. Okay, there is a sudden change of junction where it is bending down here. This junction bending down. Where this junction bending down, there is abrupt changes of junction here. So this, theoretically, they said that from Poisson equation, I don't want to go back what is Poisson equation because I will also already forgotten a bit about it. But this is actually the differential equation, okay, about the charge density over electric field, and it represents as a difference of electric field over distance, okay, distance, this distance, x. Okay, so this is, but if we solving this Poisson equation, it will obtain the electric field and also the electrostatic potential at the space charge region. So this is what happened. So actually, this is actually represent as the W, the space width, okay, the space charge width. Okay, so the potential here, if you can see here, these figures are actually showing the volume charge density. Okay, volume charge density as a P here. Okay, volume charge density in the PN junction. Okay, so if you can see at the X, towards the X, where this is the positively charged, okay, this is the concentration ND, okay, and this is the concentration NA. So this is the electric field represent as this region. Okay, so this trend, if you can see that this is actually the volume for charge density distribution at maximum. Okay, if we reach the maximum space width, it will get the maximum volume charge density. And if it has negative at negative side, okay, where the P at the P region, it will reach the maximum volume charge density. Okay, so this represent the electric field and electrostatic. Okay, so what happened here? Okay, while this one represent the electric field. Okay, the electric field. As you can see here, so if we solve this equation, they said that, so this is the continuation equation from here just now, from here. Okay, if we derive it again, okay, the differential equation, you will get that this E is approximate to the ND over electric field X plus C. So C is where the intersection. So if we plot this equation, you will get something like this, where at the X type, it linearly decrease. At the P type is linearly decrease, and it reached the what we call it as intersection here. So it looks like this. So this, okay, okay. So this is actually represent this E. Okay, E. So this is the E maximum. Okay, positive E maximum. All right. So this electric field direction, okay, we know that this electric field direction is from the N type to the P type. Okay, N type for the P type. So this represent the geometry. Okay, when there is no voltage applied, still there is an electric field flow. Okay, because of the electron diffusion. All right, so this is actually where thus this Emax actually occurred. Okay, this is actually occurred here, okay, at the junction, at the maximum point here, where the maximum electric field occurred at the PN, at the space charge region, is actually at the center of the space charge region here. Okay, here at this point. Okay, where you have space charge this XP and space charge this XN. So maximum is at the middle. Okay, at the middle. So this maximum electric field at the PN junction, actually we can calculate this. Okay, we can represent this as this equation. Okay, so finally, how to find this Emax equation? Okay, so this Emax, this electric field, Emax is by deriving this equation. So this is quite complicated equation, but then to derive this, okay, in order to get okay, how much is this equation represent? We have to derive a long equation. You can take a look at the textbook how to derive it, but that is not important. Now we want to apply the equation. So how they derive it in the textbook, I just summarize it here. It is actually considering two conditions. Okay, in the textbook, they set the potential at each of p-type depletion as a reference point, where x equal to 0 and x equal to negative xp, and the potential continuation at junction x equal to 0. Okay, finally, okay, after this derivation, they get that the potential continuity equal to this portion. Okay, but let's take a look what is actually occurred at the center. There is actually, for this case, it is a very nice drawing. It is because it is ideal case. It is going down. Okay, it is going down where the electron diffuse to the left side. Okay, but in real or ideal, that is ideal case where it is very nicely drawn. Okay, but in real case, it is actually bending down, but in curvy shape like this. Okay, curvy shape like this. Okay, where this maximum point is the built-in potential, the VBI, the potential barrier, okay, represent as this equation. Okay, so this is actually the space charge width, W, okay, W, where equal to XP plus XN. So this actually represent the space charge region. So finally, the objective is actually to get this, okay, to get this equation. So you don't have to know how it is derived, but then you need to know how to use this equation. So finally, they will get this W. Okay, this W is equal to this equation. Okay, where does this coming from? It is actually xn, this xn plus this x phi, and finally you get W. Okay, W. So this W, where does this W? It is actually from the negative xp to the positive xn, which is the depletion region or the space charge region area. All right. So when the question asks you depletion width, okay, there are two types. It's either they ask you one by one, the depletion width at n type, so you use this formula, or they ask you the depletion width at p type, so you use this formula. Or finally, they might ask you the total depletion width, which is the summation of depletion width at n type and depletion width at p type, where you use this equation. All right, let's take a look at example 2. Okay, this example 2, calculate the space charge width, okay, and electric field. Okay, and electric field. So W, the space charge width in the Pn junction. So this one calculate the space charge width W. Okay, and also the electric field Emax. Okay, usually this is represented as a Emax. Okay, and consider silicon again. Okay, so we know that silicon from the back. So the doping concentration given Na and N. So just plug in the equation. Okay, so first, okay, first you need to do to apply this equation. Okay, this equation. Okay, so you know everything, this value. Okay, you know that Na and also Nd, and also you know this Na, Nd. So now the problem is, what is VBI? Okay, I didn't show it again because when you do your revision, you have to calculate your VBI. Okay, we have seen from the previous example. So VBI is equal to this KT. I think in the previous example we have seen this KT ln what is just now? NA ND over NI square. Okay, so just plug in this, so you will get that if you calculate, you will get actually 0.635 volt. Okay, so plug in this value, you will get 0.635 and then blah 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 blah. Okay, finally you will get this equation is actually always in centimeter. Okay, always in centimeter. Why? Because the concentration in centimeter. Okay, so to be safe, okay, you will get this value. Okay, if you convert to meter, you will get 0.951 micrometer, 10 to power of minus 6 meter. Okay. All right. So next is they ask you to find the Emax. Okay, Emax. Okay, let's go back to the Emax. So Emax is represent as this one. Okay, Emax is represent as this equation. Okay, this equation. Yes, this equation. E and A electric field at the surface. All right. So Emax is represent as this equation. Okay, usually this is a common question. I think you will see this kind of question. Okay, in the test or final exam, they will definitely ask you the maximum electric field. So you apply this equation, although this equation is given, but still you need to know how to find it. So it is like a backward, okay? Since Emax is equal to xn, so you need to go back, okay? Find the xn. So xn by using this equation, so you will get this value. Okay, 0.8644. Okay, and ES here is this actually equals to the, sorry. Okay. So ES is actually equal to the ER E naught. Okay, so ER for silicon is 11.7. Okay, 11.7. E naught is I think I need to show you. Wait. Okay. All right. So E naught is actually 8.8 times to power of 14. Here, permittivity of free space, 8.8 times to power of minus 14. Okay, this one, this value. So always, I need to show this. Okay, maybe some of you not familiar with it. Okay. Okay, so like I said just now, VT where KT over E is equal to 0.0259. So where this is the value that I got from here. Okay, so I always in my slide, I always simplify the value equal to this portion. And the permittivity space, E naught is 8.85 10 to power of 14. So you use this value. And ER just now is represent for silicon. It is actually 11.7. This one, the dielectric constant. Okay, this is actually the ER. Okay, dielectric constant for silicon is 11.7. Okay, 11.7. That's why. Okay, that's why this equation. Okay, this equation represent as this, okay, 11.7 times 8.85 10 to the power of minus 14. Okay, so finally Emax, you will get negative 1.34 times 10 to the power of 4 volt per centimeter. Okay, so although this question looks straightforward, but then I have shown you step by step, okay, how to use each of the parameter, so that when you do your own revision, you know what are these all about. Okay. All right. So I need to write it here. Okay.
I'm sorry, doctor.
Yes.
So just now in the question, maybe
Uh-huh.
you will ask us about electric field or space charge, something like that. So
Correct.
we know we don't have VBI, so we have to use the equation in order to get VPI first, and then we
Yes.
apply it in W, right?
Correct.
So all the questions would be something like that. So
Yes.
I mean, there will
Yes.
be no something difficult, or we need to do extra
There
calculation.
is of course, there is. I think for this chapter, quite straightforward. I mean, for the other chapter, there will be like like VBI are given. Okay, for example, just an example. Okay, so
Yeah,
VBI are given. So you need to find the concentration, the donor concentration. Okay, you need to know donor concentration is represented as ND. So it's like a reverse question. So you still have to use this equation, but then go reverse. Okay. So you are asked to find the W. Okay, W. Okay, in
yeah,
order to find the and also in the question given VBI. Okay, for example, we go reverse. Given VBI in 0.635. Okay, how do you find how you want to find W? You know VBI, but you don't know donor concentration. Then again, you have to go back to this equation, do reverse to find the ND first, the donor concentration, in order to plug in into this equation. Then you get your space charge region. Something like that. Hello?
sorry, yes, yes,
Uh-huh.
exactly.
Something like that, Mr. Huh?
Yeah,
Are you
yes,
clear with that?
yes, very clear. Thank you
All
so
right.
much.
Okay. All right. Okay. Yeah. So these are for the example. I think okay, right? Not that difficult. I think you can follow. But then you need to try on your own the calculation. Okay. I have to mention again. You have to at least give a try to plug in your calculator, or maybe for those who familiar with the online calculator, you plug in the practice make perfect, because this is just one example. In the test of final exam, you're gonna have a lot of calculation. So the faster you calculate, the better, right? So you need to practice on the calculation. Okay. All right.
Yes, thank you so much.
Yes. Okay. Let's take a look. I think I will go like another 2 more slide and then we stop. Okay. Is that okay?
Yes, it's okay.
All right. Okay.
And also, I'm sorry, doctor. If you
Mhm.
have a list of all questions about the topic one or
Oh,
topic two, something like
Uh,
that.
uh, 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 uh. I think it would be in the textbook itself. Okay, I think let's go back here. But if you want, then I can give you some. But still, if you want to do some exercise, okay, for example, okay, in the previous chapter, students, it was chapter 4. Okay, but
Uh-huh.
this chapter, it is actually in this textbook, chapter 7. Chapter 7. 7, this chapter. So I took most of my slide in this chapter, but I simplified it my way. But then you can take a look and you can read into deep. If you think that my explanation is not so deep, but you can refer to the textbook. But if you see here, okay, so this example is actually the same like example I took from the textbook, but then I put in the slide, okay, and explain it to you. Okay, you can try on the exercise problem from here. To have more exercise on the question. Okay, so same goes to the example 2, 3, and 4. Okay, you can example 2 is same like in the textbook. Okay, where I have explained in my slide, but you can also try the exercise problem here and also try your understanding here, because they give the answer here. You can try on your own. Okay. And
That's
if
good.
you and if let's say you want more, you think this is interesting, I need to do more, you can find it here. Let's go back. So every end of the chapter here, okay, every end of the chapter, they put some exercises here. You can try on from here. Okay. exercise here. So if maybe if you have problem, you may ask me. Okay. So but basically, from what from my past experience, okay, I didn't say that I have gone through all, but the question is actually just tweak here and there. But this is actually, if you understand the concept, then you can do this lah. Basically, they tweak the here and there. For example, sketch the energy band diagram. So I think you all know. So if you want to do exercise how to sketch energy band diagram, you can try this exercise. Okay. Okay. You have your ebook right with you. Dr.
Yeah.
Michael has. Yeah, you can try on. Okay. All right.
But I'm sorry.
Hmm.
If we understand the slides and the examples in the slides, it will be enough for us, right?
Should be yes.
Inshallah.
All right,
Thank you.
inshallah. Okay. Maybe I'll give you some not tutorial question. I mean, a question that you may try on your own. Okay.
Yes,
All
thank you
right.
so much. Thank you
Okay.
so much.
Okay. Again, under reverse bias. All right. So what happened, okay, when we apply reverse bias? So we know that you are creating the diode turn off, but then there is also depletion region created. Okay, look, let's go back. Okay, let's go back here. Okay, a very far back. Where is my diode just now? This one. Okay, reverse bias. Okay, for reverse bias, as you can see here, so reverse bias means you apply voltage vice versa to the forward bias, where negative to the p type, positive to the n type, like this. And then this depletion region takes place. Okay, I said during reverse bias, the depletion region become wider, but still, although it is almost like the turn off, or there is open circuit here, but still there is something going on here, okay, in the space charge region. Okay, what happened here, okay, in the energy band diagram, it looks like this. Okay, it looks like this. Where is it? Sorry. Okay, it looks like this. Okay, so it is actually when you apply reverse bias, it is actually from p type going down to the n type. So energy band diagram under reverse bias, the p type now going down to the n type, but very very slow. Okay, because holes moving very slow. Okay, holes moving very slow. So although it is almost like off, but then there is something happen inside the space charge region. So this is what happened. Okay, now the p type going down, the bending down to the n type. Okay, for this case, all the formula that you have seen in the previous slide, you need to consider the reverse voltage. Okay, now is with the application under VR. Okay, let's say VR represent the reverse bias. So everything here, you need to consider the VR, okay, the VR. So for this case, okay, when it is potential going down here, so the total voltage, or we might say the total potential barrier, which is represent as previously, it just represent as VBI. Now we have V total, where you have to consider plus VR. Okay, instead of just using VVR value, you have V total, where you have to use the reverse voltage. Okay, and also inside the W equation, you need also to consider your VR. Okay, as well as your Emax, you have to consider your VR, the reverse voltage. So all the formula now changes to need to plus with VR. Okay, under the application of reverse bias voltage. Okay, let's take a look the example 3. Okay, calculate the W the W of space charge region in a Pn junction when reverse bias applied. Okay, when reverse bias applied. So VR. So for this case, VR is given as 5 volt. Right, 5 volt. Okay, again, for this case, this question didn't ask you what is VBI. So you have to calculate your VBI, which is KT over E ln NA and D over NI square. Okay, and then once you get your VBI, you need to plus your VR here. Okay, then finally you will get your W equal to this. Okay, remember that all the equation W is in cm. Okay, you have to convert it into meters. So finally you will get 2.83 micrometer. All right. Okay. Example 4. Okay, so design a PN junction to meet. Okay, so this is a kind of example that reverse. Okay, so you need to calculate the Emax for this case. Okay, Emax. Okay, and in this case, okay, consider the doping concentration P type is Na 2 times 10 to the 17, and then Emax is given. This is what your friend asked just now. This is some kind of question that given. It's like a reverse question. So given Emax, then you need to find the ND. So given Na is given, but we don't know the doping concentration for ND. So it is like a reverse question. So, but under the application of reverse bias 25 volt. Okay, so you have to consider this. Okay, you have to consider. Okay, Emax equal to the 2EVR blah 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 blah, and then plug in the equation. Finally, rearrange the equation. You will get that the doping concentration for donor is equal to 8.43 to power of 15. Okay, so that's why I said it may look simple, but then if you plug in the equation, you might get to rearrange a bit. Mine looks like quite like two step, but in the real calculation is like 3 or 4 steps, okay, involved. Okay, you have to take this to the left and blah blah blah, and then finally you will get ND. So you need to practice on your own on the calculation. Okay, so finally you will get ND equal to this value. So this is what it looks like. It's like it's a reverse question. You have to think a bit. You use this formula, but then you want ND now, not straightforward like ask you to find Emax, but it's like a reverse, okay, reverse question. Okay, I think that's all for today. I think we have a lot to digest for today, right?
Yes, doctor.
Yes, doctor.
I think we shall stop now. Okay. I will definitely post this recording on e-learning and also post this my final slide with my handwriting. Okay, after the lecture. Okay. Do you have any question before we stop? I hope
Thank
you
you
are
so much,
still
doctor.
okay. I hope you're still okay, hanging there with me.
Thank you, Professor.
Thank you.
all
Thank you.
right. Okay. If no
Thank you
question,
so
then
much.
we may end the class now. Okay.
Thank you, doctor.
Welcome.
Thank
All
you.
right.
Okay, thank you so much,
Okay.
doctor.
Okay. Take care all.
Thank
See
you
you
so much.
on
Bye-bye.
Thursday. All right. Okay. Bye.
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 Okay. Take care all. Okay.
You said jumpa lagi, right?
Jumpa lagi. Correct. Jumpa lagi. Betul. Okay.
Jumpa lagi. Thank you.
Okay.
Assalamualaikum.
Waalaikumsalam.